Welcome to math class. Yeah, welcome to math class. Summer's over, bell is ringing. New adventures just beginning. Gonna learn and have some fun now.
Hello, budding mathematicians. Welcome to math class. I'm your host, Mr. Lacefield, and today we are exploring the complicated relationship between the quadratic function and its inverse, the square root. By the end of this video, you will have gained an understanding of the inverse relationship through graphing, creating function tables, writing its inverse function algebraically, and determining if two functions are inverses through function composition. Today's objectives are aligned with the following Algebra 2 TEKs. What does it actually mean for functions to be inverses? At its core, inverse functions interchange the x values and the y values. By comparing the tables of a function and its inverse, we will notice when the output values from the original function are input into the inverse function, they will output the x values, or the input, of the original function. Visually, the graph of a function's inverse will always reflect over the linear parent function y equals x. Using Desmos, let's take a quick look at an example of f of x equals 1 half x minus 3 and its inverse, f inverse of x equals 2x plus 6. For the purpose of graphing in Desmos, I will use g of x in place of f inverse of x, as Desmos interprets f inverse of x as 1 divided by f of x and thinks we are defining two functions by the same name. First, I defined the linear parent function y equals x. After creating the functions in Desmos, I can compare the tables of f of x and g of x. Here, we can see that the inputs and outputs are interchanged. By activating the lines, so there's your f of x equals 1 half x minus 3 and g of x equals 2x plus 6, I can observe that the two lines intersect on the linear parent at y equals x at coordinate 6, -6, -6. Finally, by making the points visible on the graph for the original and its inverse, we can see that the coordinates are interchanged, such as 2, -2 on the original is now -2, 2 on its inverse. Now here's the catch. A standard quadratic function, like f of x equals x squared, technically does not have a single inverse function. But why not? It has to do with failing the horizontal line test. Recall that a function exists graphically when it can pass the vertical line test, which states that a relation is a function when a vertical line will pass through the graph no more than once anywhere along the graph. If we rotate a quadratic function clockwise 90 degrees about its vertex, the graph would no longer satisfy the requirements of passing the vertical line test. To determine if a graph's inverse will also be a function, we can apply the horizontal line test, which states that if a horizontal line passes through a graph only once anywhere along the graph, then its inverse is also a function. For the quadratic function, attempting to find its inverse will result in y equals plus or minus x. This is because taking the square root results in two possible solutions. Therefore, we must consider that a quadratic function will have two inverse functions. The inverses are determined by restricting the domain through the vertex by its axis of symmetry. For the quadratic parent function f of x equals x squared, the vertex is located at 0, 0, where the axis of symmetry is x equals 0. By restricting the domain to x is less than or equal to 0, which is the left half of x squared, we get its inverse function, negative square root of x, which is a reflection over the x-axis. And by restricting the domain to x is greater than or equal to 0, which is the right half of f of x equals x squared, we get a second inverse of the square root of x. When we need to find the inverse of a quadratic or square root function, we can generalize the algebraic process by following these four simple steps. Step 1, rewrite the function f of x as y. Step 2, switch the x and the y variables. Step 3, solve for y. And step 4, rewrite in function notation as f inverse of x. Let's find the inverse of f of x equals x squared plus 3, where x is less than or equal to 0, which is our domain restriction, which is the left half of f of x, meaning it will reflect over the x-axis. Step 1, we change f of x to y. Step 2, I switch x and y. Step 3, I subtract 3. Step 4, I take the square root of both sides. And the final step, I change y to the f inverse of x, and I also only consider the negative side of the square root. Now, let's consider in the second example the same function, but this time where x is greater than or equal to 0, which is now restricting it to just the right half of f of x. For this example, the process doesn't really change. We start off with y equals x squared plus 3. Making the switch, we get x equals y squared plus 3. Continuing, we get x minus 3 equals y squared, giving us the plus minus square root of x minus 3 equals y, which gives us the final inverse function f inverse of x equals the square root of x minus 3. Okay, in our next example, we're going to find the inverse of g of x equals the square root of x plus 4. Unlike the quadratic, it's not necessary to restrict the domain because it will be obvious from the graph. The square root of x only goes to the right, so all we have to do is just do the inverse without restrictions. First, we are going to change the g of x to y. Next, we switch the x and the y. Next, we subtract 4. We now square both sides. And last, we change y to the inverse of g of x equals x minus 4 squared. At this time, practice finding the inverse, applying a domain restriction if given. F of x equals x plus 5 squared, where x is greater than or equal to negative 5. Pause at this time and resume when you are ready to check your work. The inverse function will be f inverse of x equals negative square root of x minus 5. The greater than or equal means that we are looking at the right half, and by the time we are done, it will reflect over the x-axis. Alrighty, and your second practice question, g of x equals negative square root of x minus 2. Pause now to try. The inverse of g of x equals negative square root of x minus 2 is x squared plus 2. Your final practice is h of x equals x squared plus 6, where x is less than or equal to 0. Pause now and try. Okay, the final solution is going to be h inverse of x equals negative square root of x minus 6, meaning the graph will shift to the right 6 and reflect over the x-axis. There is one important exception to the rule of switching variables. In applied contexts, also referred to as real-world applications, we do not switch the variables if they have specific meaning. Generally speaking, x and y are generalized algebraic terms. If we are dealing with formulas that are already established, such as a volume of a cone v equals 8 pi r squared, we would not switch v or r since those variables have been defined. What if we did switch v for r? It would look something like this. R equals 8 pi times v squared. Then to take r divided by 8 pi, set that equal to v squared. And then finally taking the square root, we get r over 8 pi is equal to v. So on one side, we have volume equaling 8 pi r squared, but then we're also trying to say that it equals the square root of r divided by 8 pi. Volume cannot be two different functions. So therefore, we cannot switch volume for radius whenever we are doing the inverse. Instead, all we do is just solve for r. First, we would divide volume by 8 pi. That would equal r squared, our radius squared. And then we would take the square root, which tells us that radius is equal to plus or minus the square root of volume divided by 8 pi. So when you are inversing real world applications or real world formulas, all you're doing is just solving for the unknown variable. For example, if we are given the volume of a cone and want to know the radius of the cone, we would solve for the radius algebraically. In other words, we are inversing the formula. So using the volume of the cone formula, volume equals 8 pi r squared for a cone with a height of 24 inches and a volume of 5,000 cubic inches, calculate the radius. What we know is the volume is 5,000 cubic inches, and volume is also equal to 8 pi r squared. So the 24 inches height has nothing to do with the problem, so we are going to ignore that value. All we're going to do is we're going to set the values equal to each other. So 5,000 equals 8 pi r squared. We're then going to take 5,000 and divide it by 8 pi. This will cancel out the 8 pi on the right side. And that will allow us then to next take the square root of both sides. So radius is going to be 5,000, the square root of 5,000 divided by 8 pi. So let's plug this into Desmos and see what we would get. And this would be more of an approximation. So we have the square root of 5,000 divided by 8 pi. And it gives us approximately a volume of 14, or not a volume, a radius of 14.1 inches. How do you know if you correctly inverse the function? Mathematicians use composition of functions. Two functions are true inverses if the following conditions are true. F of g of x is equal to x, and g of f of x is equal to x. This is biconditional, meaning if one is true, then the other is also true. Essentially, if you plug one function into the other and everything cancels out except for x, they are perfect inverses. This informs us that we correctly inverse the function. Not only that, if we identify or are given two functions, we can use function composition to verify that these two functions are inverses of the other. For example, earlier we had f of x equals x squared plus 3, where x is less than or equal to 0, and our inverse function was f inverse of x equals negative square root of x minus 3. We can use function composition to prove that our inverse function is the inverse function of f of x. To do that, we're going to change f inverse of x. We're going to change that to g of x to make this easier to read. We will write f of g of x equals g of x squared plus 3. All we did was we took the input of x, which was being squared, and replaced it with g of x. We will replace g of x with negative square root of x minus 3. Squaring negative square root of x minus 3 undoes the negative, and it undoes the square root, leaving us with x minus 3 plus 3. Applying the inverse of negative 3 plus 3, we are left with f of g of x equals x. Our conclusion is g of x is the inverse of f of x. And because it is a biconditional statement, that means f of x is also the inverse of g of x. To wrap up, remember, swap out your X and Y unless you're dealing with real world applications, watch your domain restrictions, and always verify by using function composition. If you found this video to be helpful, please find and click on the like button and be sure to follow for future content. Thank you for watching, and I'll see you on the flippity flip.